and thank you for joining my session. My name is Pawel Rzepa, and today I'm going to show you some attacks and mitigations regarding serverless applications. Before we start, let me introduce myself. I work for Securing as a senior security consultant, and on a daily basis I perform cloud security assessments and penetration testing. From time to time, I also publish the latest news from the cloud security world, so if you're interested, I encourage you to follow me on my LinkedIn and Twitter accounts. You can also find some of my articles on my Medium blog. Okay, let's get started. Every serverless application is built from blocks of code called function as a service. The function as a service is, generally speaking, the runtime environment for executing your code. In other words, you are responsible only for providing a code without worrying on what server it is actually executed. The code execution is triggered by an event, and there are various event sources. For example, imagine you are uploading a file to your S3 bucket, and it triggers your Lambda function to handle this file. Let's say it converts a doc file to PDF, or HTTP GET request to API gateway will trigger authorize Lambda function to give you back the session token. Hope you already know that behind every serverless application stand servers on which your code is executed. So let's check out what are the main differences between main cloud service providers. AWS Lambda functions work as a lightweight micro virtual machine based on Amazon Linux image. If you're interested to find out how does the Lambda environment looks like, you can visit lambdashell.com. The project gives you a shell to Lambda environment with, of course, some restrictions. For example, you can see that the Lambda code is stored in var task directory. Using cat command, you can print the source code of the Lambda function. But what is more interesting from the security point of view is the fact that the secrets are stored in environment variables. Every instance of the Lambda function requires a role with assigned permissions, which is called the execution role. For example, every Lambda function needs privileges to put logs to CloudWatch service, or your Lambda has to be authorized to put or read an entry in dynamodb. And this is done by assigned execution roles. And the access keys that you can see in this demo belong to this execution role. And one more important thing is that each Lambda function is sandboxed, so it is separated from other Lambda functions. Let's check it out. How does the server of GCP function looks like? So here I set up the netcat listener on port 1337, on which I get the reverse shell to my demo GCP function. And surprisingly, as you can see, it is the GCP function is run under the root account, what is commonly concerned as a security bad practice. Another interesting thing is the fact that there is no access keys in environment variables like in Lambda function. But somehow this function has to be authorized to perform any action with other GCP resources, right? And the access token is actually stored in a special place called metadata. And the metadata service is accessible under specific link local address, which is 169.254.169.254. To access the metadata, there is a need to put special metadata flavor header to your HTTP request. Let's see what is the scope of this demo function. In other words, what actions this function can do. Surprisingly, by default, the GCP functions are run under editor role, giving you almost administrator permissions to all GCP resources. So, if you compromise one of such function and get this access token, then you are authorized to perform almost any action regarding any GCP resource, well, excluding the billing actions, which is pretty scary. In Azure, functions are deployed as app service. So for example, to deploy them, you have to also deploy the storage account. What is more interesting is the fact that all the functions are deployed in the same app service. So they are sharing the whole runtime environment. In other words, compromising one function will let you compromise the other ones under the same app service. All right. Let me show you how does it look like in Azure. So here I have the Azure Shell Demo app service, and I uploaded the demo shell function. It takes the CMD parameter on which you can put the Windows command. So here I can list all the resources accessible, which are accessible on this app service. And in the folder home site www-root, you can find all the Azure functions stored in this app service. Okay, so let's go into one of them. So you can see that there is the function JSON file and run CSX. The function JSON file, there is the configuration of your Azure function. So for example, you can configure there things like if this function can be accessible anonymously or requires API key. And in the run CSX file, there is the source code of this particular function. So this is my function to execute those Windows commands. Now let's print out all the environment variables, and in Windows environment it can be done using the command set. Similarly, like in AWS, you can see all the secrets in the plain text, and what is more interesting, there is also the connection string to storage account, what basically allows you for controlling all the app service. So what I will prove in later demo. Okay, the main character of the story which I'm going to present you today is Bob. Bob is a junior developer who has recently started programming serverless applications built with Lambda functions. His applications are deployed in the test environment and they will be used only internally. So absolutely nobody cares about any security testing or any special isolation of his code, what is actually a pretty common approach. Furthermore, Bob uses the most common serverless framework, to deploy his applications in AWS. The serverless framework, based on serverless configuration file, generates the CloudFormation templates, from which the application's resources are deployed in the cloud or rolled back. It also zips your Lambda function with all the dependencies. All those steps can be, of course, done manually, but the serverless framework automates most of such steps and simply makes developers' life easier. Okay, time for the first attack vector, that is dependency poisoning. Let's take a look on Bob's first challenge. Files uploaded to the particular S3 bucket should be automatically renamed with some prefix. The idea here is simple. Once the file named test new PNG is uploaded to S3 bucket, the event triggers the Lambda function. The event is basically a JSON file where you can find such information as name of the bucket to which the file is uploaded and the name of uploaded file. Then the Lambda code should rename the uploaded file and remove the old one from the bucket. Hope it is clear and easy for everyone. Like many other developers, instead of writing the code from the scratch, Bob started searching for the ready-to-use code. So he searched through the internet, through the places like Stack Overflow or npm.js repository. And luckily, in npm.js repository, Bob found the package called S3 rename. Analyzing its usage in README file, Bob found that it is exactly what he's looking for. That is, it renames the S3 file. So Bob writes the following code. As you can see, here Bob extracts the name of the bucket and then the name of the file that is going to be renamed, and then using the S3 rename package he's going to rename the file. After uploading the file test new PNG, the scanme prefix is added. Moreover, even in the CloudWatch logs, everything seems to perfectly work, so Bob is super happy how easily and quickly he was able to finish this task. But when we analyze the S3 rename package source code, we'll see there's a line with obfuscated JavaScript code. This line of code basically does the following. If there is the environment variable called AWS Access Key ID, send it to this host on this port and put the value of this variable into the parameter key. Of course, this is the IP address of the server which I control, and then it simply sends this access token to my server. And to be honest, I've created the S3 rename package and published it just for the demo of this presentation. So this is the reason why I'm collecting only access key ID without the secret, because I didn't want to harm anybody. However, there was more than 500 downloads of this package, and on my server I've received not only Bob's AWS Access Key ID, what is pretty scary. Of course, the S3 rename package is no longer available in npm.js repository, but unfortunately there are no mechanisms preventing you from putting the malicious code to npm.js. And the attack would also work in GCP and Azure. Can we do anything to defend against such attacks? First of all, by default, Lambda function is executed outside of your VPC. However, you can run VPC-enabled Lambda function in private subnet. And using security groups or network access control lists, you can control any outbound traffic. If you need access to any of your AWS resources, like for example DynamoDB, you can use the VPC endpoints to communicate with them. A similar defense approach can be done in GCP and Azure. Time for the next attack vector, that is the next threat, that is the secrets leak. The second Bob's challenge is the Lambda function should create a new entry in DynamoDB. A very common practice that I can observe in my commercial cloud security assessments is that a lot of developers store secrets in plain text. Because, well, they usually reply, who else can access it? You should be aware that the plaintext secrets aren't stored only in the Lambda function configuration. If you're using the serverless framework, the configuration file, as you remember, based on what the cloud formation with your Lambda's resources is generated, this configuration file contains plaintext secrets and is stored in S3 bucket. So anyone in your AWS account with S3 read permission can read those files. The automatically created bucket policy doesn't prevent any other user in your account for accessing the bucket with those secrets. So if an attacker compromises one of your AWS user with limited permissions, or it's a user who shouldn't have access to those secrets and want to read them, it is possible to read all those secrets and perform further attacks. To prevent such leaks, remember to always store your secrets encrypted. If you use the AWS Secret Manager, then you can refer to sensitive values with this syntax. Similarly, you can use the same concept in Azure using the Azure Key Vault and in GCP using the Secret Manager. All right. That brings us to another threat, that are the over-permissive roles. Bob's third challenge is to create the proof of concept application where internal candidates of his organization can submit their CVs. So Bob created such an application where the internal candidate can submit the URL to the CV in doc format. Once it is sent, and submitted, then the application replies with confirmation and some thank you message. Let's get back to the application and do some very basic fuzzing, like putting the bad character in the submitted URL. Based on the error message, we can see that we have the remote code execution vulnerability, and basically we can inject arbitrary comment. So here, let me show you. So here you can, yeah. So once it is downloaded, the doc file, then it is the output is pipelined to the cat doc file to make it from from doc to plain text. So if we add the semicolon, then we actually can inject any comment there. Okay, and so what attacker can do? Well, as you remember from the beginning of this application, if I print the environment variables, then I can see the access keys of the role attached to this Lambda function. And here you can see I have the AWS session token, AWS secret key, and AWS access key ID. To visualize such attack, the bad guy sends the malformed HTTP request to Bob's application and then pull out the role's access keys from displayed environment variables. Then, using those keys, the attacker is authorized to perform any action to which Lambda's execution role is authorized. And very often, this Lambda's execution role is over-permissive, and I can see at least several reasons why it is so common. One of them is using the default settings in serverless framework, which is using one shared role for all deployed functions. So imagine the serverless application which contains 3 Lambda functions, and one of them requires some permissions to do dynamodb actions and S3 service, and 2 others don't. However, compromising any of those functions will give access to this shared role. So, to avoid this, it is recommended to use a special plugin called Serverless IAM roles per function, which allows you, as the name suggests, to create a separate role for each function, which can be adjusted to needs of the single function. So always remember to follow least privilege principle. You can use the serverless IAM roles per function to adjust the permissions of each of your function. And furthermore, you can also use the API gateway request validation to validate the correctness of your request. So, for example, if you expect in the request integer value, then it will not accept any kind of injections here if you are putting any other value than integer. And in GCP, as you remember from the beginning, by default, all cloud functions are run under the editor role, which is much too much to give such permissions. But you can create unique service account to each function. In Azure, you can apply a role-based access control to assign limited permissions to the resource group. You can also use the shared access signature tokens to get limited access to other resources. As you remember from the beginning, the interesting fact is that compromising the storage account in Azure gives you the full control over Azure App Service functions. So here, let's say I want to get to execute the pwned function, and obviously I get the 404 because there's no such function. However, if I control the storage account, I have full access over the already deployed functions, as well as I can simply upload the new function. So here I'm uploading the pwned function, with the function JSON configuration file and run CSX, where there is the source code of my pwned function. Once it is uploaded, then I can go back, and as you can see, the new function was deployed. And of course, I can print out any environment variables that are stored for the need of to those other Azure functions, or I can modify them, do whatever I want. But the reality is that I'm pretty sure that there are still developers who claim that, well, this is just for testing, and on production we would never deploy such insecure resources. But the real plug of cloud world are the dangling resources. When I'm doing my cloud security assessments, I often see a lot of resources which were made long time ago just for test purpose or are related with an old, already closed projects. And sometimes those dangling resources can become a very juicy for an attacker entry point to your cloud infrastructure. An attacker can find such dangling resource by enumerating subdomains, because they all have the commonly known URL patterns. Interesting fact is that in Azure, by default, it supports the unencrypted communication via HTTP protocol. So you have to explicitly turn off the support for HTTP. Furthermore, API key, which authorizes you to call this particular Azure function, can be sent not only as a header, but also as a get parameter. Please remember that you should always avoid sending secrets as get parameters. For example, I made a simple test to check in Wayback Machine all the cached URLs containing Azure function naming pattern. And if you pass any secret as a get parameter, this secret is also cached. And in this example, as an anonymous user, I was able to get some auth token to one of the commercial application because there was cached a function with API key in the URL. So please remember to regularly audit your cloud infrastructure and remove all not used resources. To sum up, during this presentation we went through the threat of dependency poisoning. Then we went through the secrets leak over the, for example, storing the configuration files in the S3 bucket. And finally, we went through the over-permissive roles by vulnerabilities in the Lambda function. And gaining an access to the cloud is just the beginning. And if you're interested, what else can attacker do? How would look like the cyber kill chain? Then I encourage you to see my presentation, my previous presentation. And basically that's all what I prepared for you today. If you are interested in cloud security assessments or my practical AWS security training, just please contact me. I would love to hear any feedback regarding this presentation. If you see any place for improvement, please share it. All right, so thank you very much for your time. I hope you enjoyed, and see you soon in live. Thank you very much. Bye-bye.